Yeah. So today I'll be covering this deflection of beam. So it is a very, 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 very important topic for GATE. Okay, especially like in structural analysis, most of the question will come from this deflection, deflection of beams. Okay, so let me give you this brief introduction. So what I will be covering today. So first of all, I'll be covering that deflection curve. So because of any load, how this different structures, different beams will deflect. Secondly, I'll be covering, yeah, this is the same. Secondly, I'll be covering the standard deflection formulas. So there's a chart in which all the standard deflection formulas are given. So you should just take a printout of that and stick it on your wall, because that will be very, very beneficial if you learn all these formulas. Okay. Otherwise, you have to use the other methods like moment area method and different other methods to solve. Okay, but in GATE you will not have that much of time, so even they expect you to learn all these formulas. Okay, then I'll be covering some practice questions related to these deflection formulas only, these two practice problems. Then I'll cover one GATE problem, GATE 2004 problem, and it is a very, very interesting problem. It looks like very tough, but you'll see simply by using those deflection formulas you'll get to know that. Okay, the answer. And then I'll be covering one more GATE problem, GATE 2020, set 2, question number 29. This problem will also be used in this problem also. I'll also use that deflection formulas only. And then if the time permits, I'll cover some more practice questions. Okay, so try to do it with me. Okay, so in that way it will benefit you. Okay, and if you are having any doubts, you can ask me. Yeah, so let's start with today's topic. So first of all, let me briefly tell you what are the possible deflected shape for any loading. Okay, suppose, I hope you should be knowing this, but you would be knowing this, but let me just quickly revise everything. So, okay, suppose there is this simply supported beam. Maybe it may be a roller support, doesn't matter. And if we apply a load, any point load P, so it will deflect like this. I hope you would be knowing this. Okay. The thing you should keep in mind is that there will be a theta here also, and there will be a theta here also. Theta will always be there. Depending upon the location of this load, this value of theta 1 and theta 2 will vary. If it is at the center, this theta 1 will be equal to theta 2. Okay. Now, if the same kind of beam but fixed support. Okay. So in this case, the beam will deflect like this, will have this kind of shape. But here the important thing to keep in mind is that whenever there is a fixed support, theta will always be 0. Theta will always be 0. I'm sorry. Here. Okay, so that is the difference between fixed support and like hinge support. Okay, the theta will present in hinge support, but in fixed support, then at ends it will be 0. Now suppose if we have this kind of structure which is a part of a frame, then and there's a hinge support here, there's an internal hinge here, then for any loading it may deflect like this. Suppose it will deflect for any loading, it is deflecting like this. So let's call it as theta 1 and theta 2. So here in this case, theta 1 and theta 2 can be different, okay, because there's an internal hinge here. Okay, let me tell you, if this internal hinge won't be present, if it would be a rigid support, in that case the difference will be, that if it is a rigid support, let's call it as theta 1 and let's call it as theta 2. In this case, theta 1 will be equal to theta 2 will be equal to, let's call it theta. Okay, and this angle here will always be 90 degree. Okay, since it is a rigid support, previously also the angle was 90 degree, and after that, after deflection also, the angle will remain same 90 degree. If it was 90 degree before, it will remain 90 degree after also, because it is a rigid joint. Okay, but if there is an internal hinge, then these theta 1 and theta 2 can differ, they can move independently. Okay, so these few points, it is important for this deflection of beam topic. Then See how this kind of beam will deflect a simply supported beam with an overhang. So this part is known as overhang. Okay, this is a simply supported beam with a overhang. So these terminologies you should know. Okay, so in gate exam they might simply tell you there is a simply supported beam with an overhang. So you should know that what is all these terminologies. Okay, so it is a simply supported beam with an overhang. So how it will deflect? Let's see. So it will because of this support, this part will go down since it is supported at this 2 points. So it will have to be here only. After that, this thing will go straight upward because this angle we have to maintain. If it is theta, then this angle has to be theta because there is no internal hinge here. If there would have been any internal hinge, then the angle could be different. But since there is no internal, please remember difference between hinge support and internal hinge. Hinge support is like this. This is a part of a beam and this is a hinge support here. Okay, and what is an internal hinge? Internal hinge is like this is a beam and this is an internal hinge. Because of this internal hinge, these two parts can move independently. Okay, but this is a beam with a hinge support. So if this part is going up like this, so this has to go down. Okay, so this is very important, the difference between internal hinge and hinge support. Okay, I hope it is clear. So this beam, if in case of this point load, this beam will deflect like this. It will go down from here. Since there is no internal hinge here, it is it is simply a beam, so it will go up from here. Okay, so this kind of reflected shape you should know. Okay, this will help in applying these deflection formulas which I'll be discussing. Let's see for this beam. Suppose there is an UDL here. This is a simply supported beam with two overhangs. Okay, simply supported beam with two overhangs. So in this case, how it will deflect? Just try to draw it yourself. Okay, just it will go down from here since there is no internal hinge here. Okay, though no internal hinge. This is a hinge support, not internal hinge. So it will go up directly. So if it is theta, so it has to be theta here also, right? From here also, since it has to maintain the angle, if it is theta, it has to be theta here also. So it will be theta here. Let me also write it. This is straight line. Since there are no loads at the overhang part, these two parts will be straight line, while this part, since it is under the load, so this part will be curved. Similarly, this part was curved since this part overhang. If this overhang would also have some load, I'll discuss it, then it would be curved. Okay, but now since there is no load here, so this part will be simply straight line. Okay, I hope you are getting it. If there are any doubts, you can ask me then and there. Okay, now how this structure will deflect? Suppose there's a load P here. How it will deflect? It will go, you have to see that at fixed support the angle should be 0. So I have to make an angle like this, shape like this, and at hinge support there has to be some angle. So there's an angle. So it is theta here, and here the angle is 0. So here theta is 0 at fixed end. So it will deflect something like this. So you should know how the deflected shape are in this case. Now let's say for this beam I'm putting a load here. Instead of in the middle, I'm putting it here at the overhang part. So now how it will deflect? In this case, this will go down for sure. This overhang part will go down because there's a load here, but this will not be straight. Since there's a load, it will be curved like this. And since this part is going down and we have to maintain this angle, let's say it is theta. So since we have to maintain this angle, so this part will be like this. It will go up and it will be theta. Please see, if there is no internal hinge, we have to maintain the angle at both the sides. Like here we were maintaining the angle theta and theta. Here also we were maintaining the angle everywhere, because the angle is not changing. It is not change in angle means it is kind of breaking somewhere. Since it is not breaking, it is still a rigid thing. So the angle should be same. Since it is theta here, so it has to be theta here also. Okay, so I hope it is clear. Since it was going down and it is theta here, so it has, this part has to go up to maintain this angle theta. Okay, so these things please keep in mind. And now in this case, this will also be curved line. It is obviously, it is curved, right? So it is curved, can't be straight. So that upper part is already curved, but now this overhang part will also be a curved line. Okay, please note all these things. Now the very important thing, the deflection formulas, the standard deflection formulas. Now please note these things, and just download the PDF of this chart, so that you should keep it in your, stick it on your wall or something. Okay, so if there's a point load here in a cantilever beam, this is a cantilever beam, so it will deflect like this. Also, this kind of deflected shapes are important when we know that, when we want to know that where we have to keep our reinforcement. Okay, suppose an RCC beam design, what happens when we provide the reinforcement, we provide the reinforcement whenever there is a tension at that part in which tension is coming, we provide the reinforcement, right? So in this, for this case, we will provide the reinforcement on the downward. This is a beam, right? We will provide the main reinforcement here, the lower part below the neutral axis, because the tension is coming on the lower part. But for this case, we'll provide reinforcement at, for this kind of loading, we'll provide on the top part, because tension is coming on the top part here. Similarly, for this cantilever, we will provide reinforcement on the top part, because if it is, I'll make this exaggerated version of this beam. So if this is a beam like this, so this part, the lower part is under compression, and that upper part is under tension. So we'll provide reinforcement on the top part. So these kind of questions you may be asked in the interviews or something. Okay, so please keep these deflected shapes are helpful in that case also. Okay, so yeah, so it will deflect like this. It will deflect like this, and let's call it as theta, and let's call it as delta. So these values you should remember. So delta will be equal to p l cube by 3ei, and this theta will be equal to, that angle it will make will be equal to p l square by 2ei. Please note down these things and just remember these things. Okay, and if there's a moment, if there's a moment here, then what will be the deflected shape? Just try to make the deflected shape yourself also, so it will deflect like this, right? If I'll apply a moment like this beam will deflect like this. There is some vertical displacement also, and there is some theta also, right? So what is the value of this vertical displacement? Vertical displacement equal to ml square by 2ei, and this theta is equal, just remember these values. Okay, if you want to derive, you can derive also, but for a gate you have to remember these values. Now for this beam, a simply supported beam, okay, for simply supported beam, and we have, when we apply the load at the center, so here in this case, this delta, how will it deflect? This will deflect like this. There is some maximum displacement delta, and there are theta here. Since it is at the middle, so theta, both thetas will be equal. So theta 1 will be equal to theta 2 will be equal to theta. So this delta is equal to PL cube by 48 EI, and this theta will be equal to PL square by 16 EI. Right? One more important formula you should remember. There are a lot of formulas, but for these are the like most important ones. So one more, if we apply a moment here, So if we apply based on this fourth case, one question came in 2020. So which is very important. Okay, so how will this beam deflect when we apply a moment here? If we apply a moment here like this, so it is going to deflect like this. Okay, because this arrow is pushing it downwards, right? So it will deflect like this. Not made it very nicely, but let's see. So it will deflect something like this, right? So it will be, let's call it as theta 1. Since this load is not symmetrical, since m is applied only here, so these theta 1 and theta 2 will be different. Okay, so in this case question will be asked about this theta 1 and theta 2 only. So theta 1 value, it is given by ml by 6 ei, and theta 2 will be equal to, okay, just tell me whether theta 1 will be bigger or theta 2 will be bigger. You can ask and answer in the comments. If I apply a moment like this, theta 1 will be more or theta 2 will be more? You may guess, it's not a very tough question. So if we apply a moment on this side, theta 1 will be greater, right? Because it is, the load is applied on theta 1 side. So theta 1 will be greater than this theta 2. So theta 2 will be just half of theta 1. It will be ml by 3 ei. So this fourth one is really important. I'll be covering a question on based on this fourth case today. Another very important formula, just I'll remove it. This related to this UDL on cantilever. This question is also very important. So it will deflect again like this. This will be the delta, and this is the theta, right? Then the value of this delta will be WL4 by 8 EI, and the value of theta will be WL cube by 6 EI. Okay, so all these formulas you should remember. Yeah, so today I'll be covering question based on case 1. Okay, let's call it as case A and case D. Okay, now let us do a one practice problem based on these deflection formulas. Okay, so directly they won't give you a question like this only, but they will give you, so they'll do some twist on it, and then we'll give it to you. Now suppose there's a cantilever beam with a load applied at, let's say, C position. Yeah, at C position. So how will this beam deflect? It will deflect like this. Now till point C, it will be curved line, because till point C the load is there. After C there is no load, so it will be straight line after it. So let me remove this 1 meter. So it will be curved till this point, because at till C there is load, and after that, let's call it this angle as theta, and after that it will go straight line just to maintain this theta angle. So it will go straight line after this like this. It's not very straight, but yeah, till point B. So it is going down just to maintain this angle theta. Okay, because maintaining this angle is very important, otherwise it means that this beam has broken from this point. So let's call this as delta, and this, let's call it M. Okay, I hope there's no problem till now. Yeah, so till this point AC, it is a A. Case A, when a point load is applied over a cantilever. Okay, so this, for a point load applied at cantilever, the formula we know that PL cube by 3EI. So this value of delta we know, it is PL cube by 3EI. And what is the value of angle? The value of angle is PL square by 2EI. The value of this theta is PL square by 2EI. Can you quickly solve it for me? Theta and delta. What are the values you are getting? So theta delta is P. What is P? P is 5, and please see which L you have to take. We are finding out the deflection at point C, so we will take L up till point C only. Okay, so up till C, this length is 2 meter, and from here it is 1 meter. So we'll take 2 cube by 3 EI, keep EI as same, and this delta will come out to be 13.33, I guess. 13.33 divided by EI. And what is the value of theta we are getting? The value of theta we are getting is 5. What is the value of L? It is 2 square by 2 EI. So it is, we are getting as 10 by EI. Right? Now we know the value of theta and delta, but we want to know the value of delta B. We don't want to know the value of delta C. We want to know the value of delta B. What is the value of final value of delta B? Final value of delta B is this value of delta plus M. Right? This is the total value we want to know. Delta B is delta plus M. So delta B is equals to delta plus M. The value of delta we know. The value of delta we know, that is 13.33. But what is the value of M? So we know that this portion is a straight line. This portion is a straight line. This value of theta we know. Theta we know. Therefore, M will be simply equal to, when this theta is very small, that M will be equal to theta multiplied by this length. This length is 1 meter. 1 meter. So M will be equal to theta into 1 meter. So finally, our value of delta B will be equal to this delta plus M. Therefore, it is coming out to be 23.33 divided by EI. I hope it is clear to you. I hope this thing is clear. So before, if there are any doubts, you can ask me, okay? If not, I'll move towards the next problem. So before this practice problem, let us take a one gate question. That will be more interesting. So this is very, very, very interesting problem. Okay, let's see. For this linearly elastic beam, so the linearly elastic beam is shown in the figure. The flexural rigidity EI, the flexural rigidity EI is given to us when W is equal to 10 kilonewton per meter. So it is saying when W is equal to 10 kilonewton per meter, the vertical reaction RA is A. RA is 50 kilonewton. So RA is 50 kilonewton when W was 10 kilonewton per meter. Now we want to know the value of RA when W is 100 kilonewton per meter. So one could simply say that if W is when W is 10 kilonewton, if the vertical reaction is 50 kilonewton, so when W is 100 kilonewton, then RA should be 500 kilonewton, right? So if we want to see that linear relationship, if we are saying for 10 kilonewton the vertical reaction is 50, so we can some can simply guess for 100 kilonewton, since it is a linearly elastic beam, so one can say it should be 500 kilonewton simply. Okay, so 500 kilonewton is also one option here, but it is wrong. Okay, let's see how. Yeah, so let us to solve this problem, let us take two cases, right? The first case is when W is 10 kilonewton per meter. Let's see. Okay, so this is the question which is given to us when W is equal to 10 kilonewton per meter, when W was 10 kilonewton per meter. So we have seen this case, right? So this case is similar to this case B here, when a cantilever beam is subjected to uniformly distributed load. Yeah, so here there's a cantilever beam which is subjected to uniformly distributed load. Let us see what is the deflection at end B. So let's call it as A and B. Yeah. So what is the value of delta B? So delta B according to the standard deflection formula is WL4 by 8EI. Okay, so WL4 by 8EI. So what is the value of delta B we are getting? What is the value of W? W is 10. Okay, and length is 5 meter, so WL4 divided by 8 EI. The value of EI is given to us, which is 781250, right? So let's write 781250. So we are getting the value of delta B. Please tell me what is the value of delta B we are getting. 10 into 5. Great. So delta B we are getting as 1 millimeter, right? So delta B we are getting 1 millimeter. Now, please see, this means that this final deflection at delta B is this. The deflected shape will be something like this, and this delta B, the value we are getting as 1 millimeter. Since this 1 millimeter is less than this difference, the distance 6 mm. So there is a rigid support here, rigid platform here, and the distance between these two things is 6 mm. Okay, since we are getting as 1 mm, this 1 mm is less than 6 mm, right? 1 mm is less than 6 mm. So this rigid platform is not playing any role in case 1. In case 1, this rigid platform is not playing any role, so it is not affecting our answer, right? So here for case 1, we are getting it as 1 mm. So it is simply a cantilever beam with a UDL. In that case, simply our value of RA will be equal to W into length, total load, right? Total load, total vertical load. This RA will balance the total vertical load. What is the total vertical load on this cantilever beam? It is simply equal to 10 into total length, right? So it will be equal to 10 into 5. So was given in the question as 50 kilonewton, which was right. Okay, just this first part I just solved to let you know the significance of this 6 mm which is given to us. Okay, now because in first case we were getting reaction simply as 50 kilonewton, because this the total deflection which we are getting at the end is 1 mm, and this means that this cantilever beam is not at all getting affected by this platform. This platform is here or not, it doesn't matter for case 1. Okay, so if there is any doubt, please ask, let me know. Okay, now in the second case, when W was equal to W is equal to 100 kilonewton. In that case, let's calculate delta B. So delta B from the standard deflection formula will be equal to WL4 by 8 EI. Okay, so delta B will be equal to, what is the value of W here now? W is 100 kilonewton. Let me make it. Please solve this for me. W, great, great. You are getting 10 millimeter. So delta B we are getting as 10 millimeter. So this 10 millimeter is more than 6 mm. What does it mean? It means that this this platform is now playing a role, because when this beam is deflected like downward like this, now in the middle only, like in the at the 6 mm only, it could not deflect by 10 mm. In the middle only, this thing came, right? Okay, so it means that now, because of this 100 kilonewton load, this cantilever beam has now become simply supported at the other end. So although it is not, so yeah, it is not very straight, but you can imagine like this. It was going down like this, but in the middle only this platform came, and now it is not at all a cantilever beam. It has become a simply supported beam. Let me draw it like this. Okay, so this beam, because of that 100 kilonewton load, was trying to come down, was trying to deflect like this by 10 mm, but in the middle only this platform came. So now there's no gap between this platform and this beam. I hope you understand, right? Because when there was of 10 kilonewton per meter load, this platform was not affecting this beam. But now, since it is loaded with 100 kilonewton per meter, this platform is playing a role now. So this platform, this part of beam, that is part B, is now supported at this platform. Okay, so now what is the value of reaction. Now this value of reaction Ra, this is not the only support. Now this A support is not the only support. Now we have this support B also, right? Earlier in a previous case there was no support at B, right, because the loading was very less. But now since it is loaded at 100 kilonewton per meter, so now this support is also there because has deflected by that much amount. Now it is settling on this support, just imagine it. Okay, so now there is this support B also, so there will also be a reaction RB. Is there any doubt on this, why this platform is now playing a role? Because the loading on the beam is so large that it has deflected the beam by more than 6 mm. Okay, so that is why this platform is now playing a role. In this case, now the reaction will not be simply equal to Ra equal to total load. The reaction will be equal to this Ra plus Rb equal to total vertical load. So total vertical load in this case is 100 kilonewton per meter, and what is the length? Length is 5. So here Ra plus Rb is equal to 500 kilonewton. The total load is now 500 kilonewton. Now, what is the value of Ra and Rb? Since it is a uniformly distributed load, so Ra will be equal to Rb will be equal to total load divided by 2. So these two Ra and Rb will take 250 kilonewton. Okay, so Ra will also be 250 kilonewton and Rb will also be 250 kilonewton. So that was the significance for this question, for this 6 mm gap which is given to us. If in case, because of this loading also, because of this 100 kilonewton loading also, if the this let's say if this platform distance is 16 mm. Okay, if it would have been given 16 mm, then what you would have been doing, you would be doing like by 16 mm, 16 mm is greater than this 10 mm. So in case 2 also, in that case this platform will not be playing any role. In that case this would have been simply 500 kilonewton, because then RB would not be playing any role. I know this is a little bit confusing. If you have any questions, you can ask me. From my side, I've explained it very clearly. Any questions? Or it is fine? Okay, it's fine. Maharini, is it fine? Okay, just practice. See, they are not giving direct formula based questions, they are twisting a problem a little bit. Okay, so these things you have to keep in mind. Yeah, now this question. This is a GATE 2020 question of set 2, question number 29. So in this question, the planar structure RST is given to you. It is simply supported. This is a hinge support. This is a roller support here, and this part TS is there. And now then we have applied this load P at point T. So the members R, S, and ST have the uniform flexural rigidity EI. S is a rigid joint. So if they have mentioned that this edge is a rigid joint, okay, there's no internal hinge here. Consider only the bending deformation and neglect the self weight and axial stiffening. So any axial deformation we have to neglect. We just have to consider the bending deflection deformations. So what is asked? So when the structure is subjected to a concentrated horizontal load, this load P, at the end T, the magnitude of rotation at support R is. So if for this kind of loading, they are asking that what is the rotation at this support R. Okay, so this is the question. For this kind of loading, what should be the rotation at R? So first of all, let's see what should be the deflected shape. This is R, this is S, this is T, right? So let us make a quick free body diagram, although it is not very necessary here, but let's make it. Okay, so this is R and this is S So to get to know what is the moment that is coming at S, I'm drawing this free body diagram. So I'm just separating this part from here. TS, I'm separating. This is part TS, this is S. Okay. So we are given that this load P is applied here. Okay, so this load P is applied here. So just to balance the horizontal, what do we do in free body diagram? We balance all the conditions, right? All the loads. So this P load is acting here. So this, to balance this P load should act in the second location but in the opposite direction. So this is all about free body diagram. So this load should come like this. Okay, it is now balanced. Horizontal load is balanced, right? In both the direction we have load. Now, because of this applied load P, we will also have a moment here. And what would be the direction of this moment? The direction of this moment will be opposite to what this load P is trying to rotate. So this load is trying to rotate this part TS in the clockwise direction. So we will have anti-clockwise moment in the opposite direction. So we will have moment like this to balance it. So it will be like P, what would be the magnitude of this moment? The magnitude of this moment will be P multiplied by the length TS. So P multiplied by the length TS is L by 2. So P L by 2. So this is all about the free body diagram. Now this load P is applied at end in this direction, right? To balance it, we will apply the load here in the opposite direction P. Now this moment is applied in anti-clockwise direction. Therefore, we will apply a moment here in clockwise direction and the moment is PL by. This is all that was important, just to know the forces at point S. Because of this load P, I have made this free body diagram. Please practice this free body diagram also. If you do not know this drawing this free body diagram, please let me know. I may cover some session for that also. Okay, so this free body diagram, I just draw it to know what are all the forces that are coming at point S. So at point S, there is an axial load P and there is a moment which is PL by 2. Okay, so this is all I want to know. Now, the next thing is, in the question, we are asked to know what is the value of rotation at point R. Okay, so that we want to know. So let's draw the deflected shape for this beam. And also, one more important thing, we are given that we do not need to consider any axial deformation. Okay, so I am not considering the effect of this load P here. Now, for this moment PL by 2, what would be the deflected shape? This arrow, just to know the deflected shape, see how this arrow is moving. This arrow is pushing this part in upward direction, S part in upward direction. So the deflected shape will be something like this. Deflected shape will be something like this, because this arrow is, it will move it upward. Okay, so this is the deflected shape we are getting. See, this is the same case as we discussed, this case D, in which there's a simply supported beam and we applied a moment M at one end. So this question similar to case number D. So this is the probable deflected shape for this beam. So we need to know this value. So there will be some theta R and theta S here. So we are asked the value of theta R. So we know that what is the value of theta in case when there is a moment applied at one end of simply supported beam. The value of theta in the far end will be ml by 6 ci from the standard deflection formulas. It will be ml by 6 ci. You know all the values. You know the value of m, which is pl by 2 into l u divided by 6 ei. So you are getting the value of theta r. Yeah, for the far end it is ml by 6 ei. far end, yeah, F. Because at the near end, because when we are applying the load here, na, at S. So at S we are applying the moment. So S deflection, rotation at S will be greater than rotation at R, right? So ml by 3 EI is greater than ml by 6 EI, right? So that is why for far end the reflection, the rotation will be ml by 6 EI, and for the near end, that is the end at which we are applying the load, it will be ml by 3 EI. So theta R will be finally will be PL square by 12 EI. This is our final answer. See, it was very simple, but only it is simple for those who know this formulas, right? ml by 60 and all. So the answer is PL square by 12 vi. That is option number B. That is a GATE 2020 question, very just 2 3 year back. Okay. So we are getting just you can they may ask you the value of theta s also, because it will be calculated in a similar manner, but just it will be ml by 3 EI. Any other doubts? Yeah, yeah. Do you want me to explain it again? Uh-huh. Because in free body diagram we have to in you want to ask something? Okay, okay. So either you can so there are two methods of doing this. One is to draw the free body diagram, and one is to simply there's a method, like don't know if you know that or not. Whenever there is a load applied at some distance away and you want to shift that load, what you can do is you can simply shift it here, like you can shift it here P, and you can apply a moment like this. Sorry, moment direction is wrong. Moment like this. So either you can do that simply, from that you don't have to draw any free body diagram. Okay, so this is one method. Suppose I'll just explain it again. Okay, suppose there is a load W which is given to you. Okay, if you want to shift the value of this load W, what you can do, you can simply shift it. You can just remove it from here. Okay, just for calculation purpose, you can remove it from here like this, and you have to apply a moment now also. And what will be the value of this moment? The value of this moment will be that the load you which you shifted multiplied by the distance which you shifted. So suppose let us call it as L, so it will be WL. So that is one method of this is just for the calculation purpose. Okay, you can do it like that also, but this is one method. But if you are asking for the free body diagram method is more conceptual, you can say. So in this method, why I applied this moment, because in the free body diagram, for that particular structure which you break from the total structure, that particular structure should be balanced in everything. Okay, so all the forces should be balanced, vertical direction, horizontal direction, and the moment should also be balanced. Okay, so this was the load P applied. So in the second end I have applied this load P. Okay, but this load P is also causing a moment. How much? Because it is trying to rotate this thing. If I would not have applied this PL by 2 here now, so it would mean that this part would be rotated. It has formed a couple now. Just I'll remove it. Please see that part TS. It has formed a couple. Huh? So it is trying to rotate. It is not in equilibrium right now. Is it or is it not? No, right? It is trying to rotate this TS part in the clockwise direction. If I would not balance it, then this means this is rotating like this. Huh? This is not in equilibrium. Although the horizontal forces are balanced, but still it is not in equilibrium because rotational part is not balanced. Therefore, to balance this, I have applied this. We have to apply this moment also. And what is the value of this moment? The moment will be force multiplied by distance, TS. So it is PL by 2. Now it is balanced. Now it can't rotate, because if this value of P, if this load P is trying to rotate it, this PL by 2 will balance it. So overall it is balanced now. I hope it is clear now, Harini. Any free body, if you are drawing the free body diagram now, you have to balance it in everything. If you have not applied this load p, sorry, this moment, then it is horizontal. Okay, like if we just see the horizontal load, it is balanced. Okay, it's because p is balancing p, but the moment is not balanced, it is still not stable, right? It will rotate in clockwise direction. That is why, if you do not want to do this free body diagram and all, although you should know it because it will help you in other problems also, you can simply just shift do this load shifting method. Whenever you want to shift a load, you just shift a load, you just remove it from here, you shift a load by some amount, and you can apply the moment p l by 2, and the direction of this arrow should be same as this part. Like, if you are shifting the load from this side, the direction of arrow should be this side. If you are shifting the load from this side, then the direction of arrow should be this side. I'll just show you one more question. Just try to do this question. It is very very similar. Just you need to find the slope at a. Just try with that load shifting method only. Just try to solve it. You have to find theta a. Very very similar question. If you understand the previous question, you'll surely do this. You can either use the free body diagram or the load shifting method, which I told you. Should I solve it or you are trying it? So let me first use the load load shifting method. So it is a simply supported beam here, and we have this load W. So if you want to shift this load from the overhang part, so you can simply remove this load from here, put it here, W. But you can't just simply shift the load, you have to take the moment effect also. So in this case, the arrow will be on the right side. Why on the right side? Because you have shifted the load from that side. So the value and the direction of this arrow will be like this, and the value of the moment will be WL by 4. So this is very simple. Now what is the value of theta A you are getting? Okay, let me solve it. So for this case, the deflected shape will be roughly equal to this, because this arrow is trying to, no, this will be the deflected shape. You can draw it with this part also if you want, but it's not very important because you need to find the value of theta A. So it is theta A and it is theta B. So what is the value of theta A? Theta A will be equal to ML by 6 EI, right? So theta A will be equal to, what is the value of M? It is WL by 4 L divided by 6 EI. Finally, the value of theta A will be equal to WL square by 24 EI. I hope it is clear to you. Is it clear, Harini and Mayur? Cleared now, no? So you can, if you don't want to use that free body diagram, you can simply use this method of load shifting. Okay, then if it is clear, so practice all these questions. Yeah, just note down this question. In this question, you need to find the value of delta B as a practice question. This kind of question can come in the exam. Although this question is not based on the deflection formulas, just take a picture of it. Okay. So this topic is very important. There are charts available for these formulas, because today I just covered these case A and case D only, and some part of case B also you can say. But they can ask you any questions and they can twist the problem. But in any problem, these kind of formulas they can you will be asked. Okay, so please practice all these things. If there are no doubts, I would like to stop the session for today. Okay, please ask me questions, whatever doubts you are having. Okay, there's no stupid question. Okay, you can ask me anything. Okay, then thank you so much. Okay, thank you.